I want you to think about different types of industries now. So when we think about industries, I mean, broad sectors of business. And I want you to think about what of the first three, let's take the three CIA, which of those threat types would match the greatest intensity for given sector? So let's start with service providers. That'll be A. Internet service providers. What would internet service providers be concerned about as their primary threat? Second would be software developers. What do you think software developers would consider their primary threat? And third, identity providers, identity vendors, people who are dealing in identity, checking your identity, checking validity, and so on. So we have ISPs, software, and identity. In those three sectors, which do you think? Well, let's take a minute, let's think that through. ISPs provide service, right? They have to be up. Like the worst thing that can happen to a mobility or internet service provider is to be down. So the availability threat turns out to be the most intense for that group. Now let's take software. Software, I'm providing you a piece of code, I want it to work. So as you'd guess, integrity is an enormous consideration in software development sector, right? You don't want infected code. And then for identity, where I'm trafficking in information, confidentiality is a big issue, right? If I'm checking validity, I probably have all kinds of customer records. I want to be very careful about exposing information about your identity. So you can see those are three industry sectors with somewhat different concerns, but notice all three of them would be concerned with every threat, right? I'm more asking you, what's the primary concern? And in the three cases, I think it should be somewhat clear. So I hope that's helpful. Let's keep that CIA model in mind, and let's recognize that in some cases there may be a fourth. Thanks. I want to talk to you about the disclosure threat. Now, you'll recall that disclosure is about confidentiality. And usually the best way to get some deep insight into these types of things is through a story. So this, I think you'll enjoy this kind of fun, little different story. Here in the United States, we've had problems with political parties protecting data. And as I speak to you now, roughly 20 years ago, back in the mid-90s, the Democratic National Committee, so here in the United States we have Democrats and Republicans, but the Democrats actually called me concerned that email security might be something that would cause them to lose an election, and they wanted to know if they could have some help producing more privacy in their email. How funny is that? Because 20 years later, you could argue that had they had better privacy in their email, might have had some differences in the way elections and so on have gone. But at any rate, let me tell you about the story. So I had two buildings that were connected in Washington, D.C. by a telecommunications line. The way it worked in those days, it would be a private line connection out to the ISP, like a phone line in a sense. And what they were interested in was putting encryption at either end of the line. Now, here's the idea. A lot of disclosure and confidentiality problems are fixed by a technique known as encryption. We're going to talk about that at length in these lectures, but the idea is that you garble or scramble what's going on between two buildings, between two people, between two entities, two computers, whatever, or a group. You garble it. The idea that if somebody comes along in the middle and listens, puts a tap on your communication, then they won't be able to understand what's there. Does that make sense? Like if you and I were together in a room and we're talking the way we're talking now, if somebody's sitting next to us and they're listening, then they understand what we're saying. There's no secrecy at all. In fact, here in the United States, we have laws that say if you and I are sitting, say, in a Starbucks together talking, and we're jibber-jabbering back and forth, and somebody's sitting next to us, they have every right to listen. Now, you may be in a country where that's different, but I think that's pretty universally the case. That if you're in a public square, then you can listen. You're there. If you don't want anybody to listen, go somewhere else. right? If I want to go hide somewhere in the corner and have a private whispered conversation, then again, here in the United States, we have laws that say, you and I as friends, if we want to have a private conversation, the government's not going to come put a big boom microphone over our head and listen. Again, you may be in a country where that'd be different, but you get the idea that confidentiality and disclosure are about this idea of communication. Now, back to sort of the Democratic story, they were concerned about, the communications between their two buildings and putting some sort of encryption between the two, which I think makes perfect sense. Now, putting that encryption, as you'll see, is not so easy. Like you have to figure out where you want to do it. Do you do it on everybody's handset? Do you do it on all their computers? Or do you go into the basement of the two buildings and do it on the wire that goes out of the building? Now, in the first case where you do it all over the place, that's called end-to-end encryption or end-to-end secrecy. That's a way of enforcing confidentiality properties between individuals, regardless of the systems that they're using. That's one approach. And the advantage is it works better. The disadvantage is way more work. If I did it at the basement, where the wire is coming out of these two buildings to connect to each other, that's called link encryption or link secrecy, where between the buildings, I garble stuff. So if, within the building or within some network or some enclave, I hope there's all good people there. We can say that that's very closely related to something we call a perimeter model. But as long as it leaves the building, then I make sure I have secrecy. So as you can see, this disclosure property is certainly more involved than just things leaking. The way that we solve this is going to be a combination of different architectural concerns and certainly of using functionality such as encryption. Now, what I'd like you to think about is maybe from an organizational perspective, if somebody's giving you advice, as I did 20 years ago on this encryption, what would be the circumstances under which you may either do it or not do it? Like, for example, if you're running a business and I came along and I said, hey, why don't you put encryption on all your stuff? You should be worried about disclosure. Well, what would you do? Would you just immediately take the advice that I provide, put the encryption in place, put link and end-to-end encryption, do all this stuff? Or would there be other considerations that would come to mind? For example, cost. Does it cost a lot of money to do this? A lot of time? Does it affect our communication? When we're talking over the phone, if I put encryption, does it suddenly sound like we're both talking to each other through a tunnel? These are basic ideas, and as we go through the threat types, you're going to see that if I want to counter the disclosure threat, it doesn't come for free. There's going to be things I have to do to counter that, and that's what I'd like you to ponder as part of our sort of, as you think through this session, think about the conditions under which you might actually take the time to dramatically reduce the risk, in this case, of disclosure. Thanks. So now I want to talk to you about the integrity threat or modification threat, the threat that somebody might be corrupting an asset, a piece of software, a system, whatever, for malicious purposes. And the obvious example here is malware. That's where code that has some presumed correctness or validity has that corrupted by a malicious actor putting malware into your system. Integrity threat. Now, how in the world would you do something like this? Well, again, it's the permissiveness of the CPU memory model that's been in computing since we've had computers. This idea that, I can take code and I can manipulate it and make it do other things by just shifting and changing. We don't have rigidity in computing. We have the ability to make modifications to software. Think about that. That is absolutely fundamental to this whole thing. If you drove up in a car into my driveway and you say, here's my new truck, there it is, what do you think? How easy is it, or would it be for me to make fundamental modifications to that truck? Probably not easy, right? I mean, it's hardware, there's components, they're all connected up. Maybe if I'm a genius mechanic, I can make some changes, but it's certainly not a flexible, easy environment for making changes. Software is different. If I show you a piece of code and I say, hey, what do you think? and you look at it, you want to make some minor changes to it, we're well set up for that. Now, one of the problems that occurs frequently in programming is the handling of buffers. Now, here's something for those of you who are programmers will be very familiar with this idea. We use scratch space in memory in a lot of our programs to keep track of things. So for example, if I'm pushing to a stack and I want to add things, then what I might do is I might push the first value to a little scratch pad in memory, then I push the second value to that scratch pad in memory, and then my program might pop the first one, pop the second, add them, and then push the answer onto this buffer, onto this stack, onto this scratch pad in memory. So we're constantly using memory to do things. And one of the things that was invented with computers is if I look at a full list of memory in a computer, then what we typically do is we reserve some portion of that for the programs you run, and we reserve some portion of it for the data that your program uses. That makes sense? Memory keeps track of programs and data all in the same place. Yeah, it's in different places in memory, but it's the same sort of linear progression through memory. It's a basic weakness that we've had in computing since the beginning. Now, here's the way programmers might cause an integrity threat through something we would call a buffer overflow. The way that works is, up here in your program, I'm reserving somewhere a little piece of scratch pad to do something. And I reserve a little piece of memory where I'm going to put some array of 10 characters or something. But what I do really is the program then, instead of just putting a variable that's within those bounds, I put some gigantic thing into it, some gigantic piece of data that not only fills up the buffer or scratch space that you put in there, but it overruns and starts causing all kinds of problems in memory. And what's going to happen to your program? It's going to go, it's going to explode or crash. And again, the way computers work is that when your computer crashes, the program counter goes to something called an exception handler. That's the way a computer works. Program runs and it goes for whatever reason, and the computer goes, what do I do? Well, the designer says, well, what do we do whenever something crashes? Let's put the program counter here and run this code to recover. You got that? Program crashes, program counter, recover. Okay? Now, what if, and this is going to sound crazy, but this is the way it works. What if instead of overwriting the buffer a little bit, I really overwrite the buffer? I mean, overwrite it all the way down to the point where I find the recovery procedure, and then where the recovery procedure is, I put a piece of code that I want to execute. You got that? So here's the idea. I overwrite the buffer, and I overwrite it with, we would call it no-op. Put a bunch of things in there that really don't execute, but I just start filling up memory with no-ops. I get to or even go past where the recovery procedure is, and then I put code at the appended part of that no-op bridge that runs what I would like to do, maybe copying me a shell. So now here's what happens. We're in a program. I overflow buffer. The buffer overflows with a no-op bridge that fills up memory and then has something I want to run. The whole computer goes, crashes, goes, oh my gosh, everything goes haywire. The program counter goes down to the recovery memory address, but I've overwritten that with no-ops. It's going to ride the no-op bridge, find my piece of code, execute it, and I probably now own your machine because I put code there that will own the machine. Isn't that clever? Look, there are a lot of resources on the internet, and we'll make sure as part of the support environment here for this lecture that you have some things that we recommend that you take a look at, including a great paper called Smashing the Stack for Fun and Profit. You can take a look at, and you can dig in and try and understand buffer overflow on a little deeper level. But I think you probably get the idea here that integrity threats generally involve problems in memory, the fact that data and programs are all sort of interspersed, and I can have things overwrite, and I know where control will go when things crashes, and on and on. I can take advantage of these things to cause integrity problems in computer systems. So ponder that, think about that a little bit, and we'll see you on the next one. Now, I want to talk to you about the availability threat, and in particular, this denial of service condition that we try and avoid. Denial of service is when someone clogs up or blocks or maliciously attacks the ability of somebody to gain access to a resource that they're authorized to gain access to. Let's take an example. Generally, if you're listening, let's take a non-computing thing. As a human being, and I'm trying to listen, I'm trying to pay attention to something, a way that I can make it difficult for you to listen or pay attention is to create a whole bunch of noise, right? Like you've all had that experience. If I'm trying to listen to something and there's tons of background noise, then I go, turn all that stuff off. I can't hear. There's noise coming in. And that's an important concept because much of denial of service is based on this idea of lobbing a whole bunch of noise so that you can't pay attention to or accept real service requests. Now, one important property here involves sort of this idea of amplification. So I do something and it amplifies. Like think about if I was hitting a tennis ball at a wall. Well, we're used to hitting a tennis ball at a wall and one tennis ball comes back. What if I could hit a tennis ball at a wall and 1,000 tennis balls come back? That's amplification. And an example would be if I query some system, little simple query, I say, hey, what time is it? And you say, 2 o'clock. I go, great. Little question, little answer. Everything's great. But what if I say, what time is it everywhere in every language? And I'd like to know what time it's going to be every time for the next 3 months in 1 second intervals. So what's going to come back? Oh, it's crazy stuff. You're going to get all this time information hitting. You go, all I did was ask what time it was the first time. I go, a little answer. Then I hit a tennis ball at a wall. I got all these tennis balls coming back. That concept of amplification is absolutely fundamental to denial of service attacks, the ability to have something small become something large. Turns out the internet is chock full of these kinds of examples. And furthermore, there's a second property called reflection, where I can have me hit the tennis ball, but guess what? The ball hits somebody else instead of me. You get the idea? So I hit tennis ball at the wall, doesn't come back to me, it hits you. And now, how about this? A tennis ball at the wall, and now 1,000 tennis balls hit you. That's a denial of service attack. That's how it works. So now I say, hey, what time is it? But I ask as you. And then you're sitting there and all of a sudden you hear 2 o'clock and you go, 2 o'clock. What? I didn't ask anything, but it's no big deal. It's one little answer. But if I ask that other thing, all the times and everything, and all of a sudden you're being barraged with the time, then you're essentially experiencing what we would call a denial of service attack. Now we're going to get into later how distributed denial of service attacks work and how botnets accomplish these kinds of things. But I wanted you to have the basic idea here of denial of service and how it plays out. Now, it's kind of a little quiz to test our learning. I want you to think about a few little properties here that affect the availability of a system. And I want you to think in your mind which of these, based on what you've learned so far, kind of constitute an attack, a cyber attack, a denial of service cyber attack. First would be if lightning hit a data center. Suppose the data center gets hit with lightning. And you can imagine probably would be taking out the data center's ability to process data. So that's A. B would be some software that's intentionally taking out access points, Wi-Fi, 4G, LTE, whatever, but intentionally blocking or taking out access points. And the third would be coding errors and unintentional coding errors that cause a system to crash. So we have lightning in a data center. We have software on endpoints that are taking out access, and we have unintentional coding error. Let's take the three in turn. Lightning, we've said earlier, is not a security issue. So I want to make sure you have that in your mind. When there's something that's non-malicious, non-intentional, it takes out a data center, a problem, but we don't consider that denial of service. The third one that we said, unintentional software, again, If it's unintentional, it's not a security issue. Security implies intentional, deliberate, malicious. So obviously the middle case is the one that we would consider to be a denial of service attack. That's where endpoints are taking out an access point, taking out Wi-Fi, flooding it, making it unavailable for authorized users. So you can see in those three cases, whenever you see something that looks unintentional, unavoidable, nothing malicious, not security. But in the case where it's malicious, there is. So keep in mind also that idea of amplification and reflection, because we're going to come back to that. And as we get into some of the more technical discussions around denial of service, you'll see that those are fundamental properties. So thanks. Now, I want to talk to you about that special case threat type that we alluded to earlier, namely fraud. And you can also call it theft. And just to review, that's where you steal something, you're not paying money, but you're just basically taking an asset. And this is an important kind of consideration in cybersecurity because increasingly with things online and with so much e-commerce going on, this idea of preventing people from stealing is a really big piece in cybersecurity. So we do want to take a minute to think about the threat and how it normally plays out. And as we said earlier, when somebody is committing theft, they're not paying for a service. And the first sort of place that we can take inventory where this might happen is any place where there's something of value. So if you're doing an inventory about whether there's a fraud risk, then it's simply, is there any financial value in something that's being protected? Financial value is what attracts fraudsters, okay? If there's no financial value, then as the security engineer, as the security analyst, as a security expert, you know that fraud is probably not going to be the big issue. But when there is financial value, then what we need to do then to prevent this, and we'll get into it later, but I want to give you some motivation now for the cybersecurity concept, is we need to look for hints that fraudsters would typically follow. Does that make sense? Like we're going to do something that would be called behavioral analysis. That's where I'm watching the behavior of something and I'm trying to determine whether fraud is being committed. I'll give you a simple example. Let's say we're keeping track of passwords that are coming into a system, okay? So you write a program and I watch and I see user ID, password, and I check and I see, oh, wait, not valid. And I send a response back and go, not valid, sorry. And I sit and I wait. Now the same user ID comes in again. Another password comes in, it doesn't match. And I go, sorry, not valid. It's 2. Then you see another user ID come in. I see another password, and it's not valid. And I go back and I go, hey, not valid. Now the question is, from a behavioral perspective, can I make some conclusion about those 3 guesses or fat fingers or whatever? Whatever's going on, somebody's having a little bit of trouble here. They tried 3 times and they didn't know the password. So here's the question for you. Are they committing fraud or they just forget their password? It's a big deal in cybersecurity. It is absolutely fundamental to almost every control we have in cybersecurity that an attack, in many cases, may not be an attack. We call that a false positive if we call it an attack, but it's not. We'll get into that later. But for now, this theft fraud issue is something that's a little tough to know when something's committing fraud. Look, a lot of you have probably had experiences with your banks where you get a phone call and they say, Mr. Jones, Mrs. Smith, oh, we see you're using this credit card in Singapore. Are you in Singapore? Is this okay? Are you really buying a suit in Singapore? It seems like you don't live there. Is this okay? They're doing behavioral analysis to determine if something doesn't make sense. You've all had that experience. And a lot of times it is a false positive where you say, well, yeah, I am in Singapore. And yes, I am, buying this suit. Thank you for checking, but everything's just fine. You get the point? So it turns out that fraud is something a little difficult from a foundational perspective to really assign good, solid safeguards to, generally what we do is we watch the behavior, we look for things that are odd patterns. One other example that we see often in fraud activity is when somebody's going through a website that might have a wizard, for example, where I'm stepping through the wizard, doing each of the steps. I go to this screen, then it says continue. I go to that screen, I do continue. Fraudsters usually don't have a lot of patience, and they can usually find a way to skip through a wizard. And a lot of anti-fraud systems online will watch to see if you've skipped a wizard and say, that's probably fraud, and it may or may not be. So I think the learning here is that where there's money, you have to be suspicious that there may be fraud or theft that can go on. And for the most part, the types of technology and the types of safeguards that we'll use to reduce the risk of fraud are going to be rooted in behavioral activity, just as you've seen with your credit card company. So thanks. Now we're going to talk about cyber attacks. We're getting towards some material that's getting a little bit more technical. What you're going to find is that a lot of the upfront material here, as we do taxonomies and so on, and my stories, my incessant stories, will lead to or build a base so that we can start doing some computer science. But for now, I want to help you understand how a cyber attack is organized. We're going to take the view of the defender, okay? So when a defender is watching a cyber attack, what we see are something called indicators. That means we see some hint or some idea that there may be something going on. For example, if you're sitting at home and you see a car drive by and you go, car drive by. I wonder if that's a problem. What question is, would you call the police then? I don't know. It's an indicator. You might have a little bit of a weird discussion with the police if you said you saw a car drive by. Let's say a few minutes later you see a car drive by again. Now do you call? You get the idea. You're going to see these indicators that may or may not lead you to believe that you're under attack. And what happens is these indicators build up to some threshold where really an attack has occurred, after which the indicators you see might actually have some real damage. Like you might be noticing that assets are really being damaged. There's real problems with something. So we tend to break attacks into two phases. There is the early indication warning phase, and then there's kind of a post-attack phase. We say there's early and there's latter stages to an attack. Now, keep in mind, anybody would say you're better off stopping an attack in the early stages, right? I mean, that makes perfect sense that you'd want to stop it before it gets to the point where there's an issue. Like if I call the police because the car drove by a couple of times and they really are criminals, then that's fantastic. I've stopped it. I didn't wait until they came up to my house and broke in and stole all my stuff. Well, if you call the police then yeah, I understand. They broke into the house, broke all my stuff, they're stealing things, I call the police. Would have been better if I'd called when they drove by. Well, what's the problem with calling in those early stages? And what's the problem if you're a cyber defender with initiating incident response based on early indicators? It's called false positives. That's where most of the fuss that I'd be making about a cyber attack would be not really a cyber attack. I'd be making a fuss about a lot of nothing. So in our minds as cyber defenders, we try to organize cyber attacks in a way that helps us be preventive, but also balance the amount of time that we want to spend with all these indications and warnings that may be popping up and with issues that'll pop up in the different phases, and make sure that we're not wasting all of our time. Now, the way an offense will think about cyber attack is they're going to do things like reconnaissance in the first stage. Then they're going to do scanning to try and see what's going on your system. Then they're going to gain access to your system in some way. Then there's going to be a real exploit, and then they'll probably cover their tracks and leave. That's the compendium that an offense sees. The defense just sees a bunch of indicators. The offense is not going to mail you a map of what they're doing. It's much different. So I want you to think that as a defender, you do not have a map of what the offense is doing. They're not laying it out for you. It's like being in a dark room and feeling around. That's what it's like to do cybersecurity in a practical setting. That imagery is an important one. Dark room, feeling around and trying to understand what in the world is going on here, what sorts of things are happening, and really that in essence is the core problem in cybersecurity. If we knew what the offense was doing, then we'd be fine, but it turns out that we don't. We'll see you next time. There's two different types of attacks that we see in cybersecurity. The first is called brute force. That's where an attacker creates software, creates a system, creates some sort of an attack strategy that's literally going to try every possibility in some input set to try and break into your system. The obvious example here is passwords, right? So one possible way to break your password is try every password. I know it sounds crazy, but that's why we try and lengthen the password that you're using, make sure that it's of sufficient length and complexity, that it's not easy for you to just try every possibility. If you have a 3-character password, then in my sleep I can write a program that will try all possibilities of 3 characters. So brute force attacks, it turns out, are things that are thwarted in cybersecurity by making size to domain. Now keep that in mind. Size becomes a means for dealing with brute force attacks. When someone asks you, hey, what's the strength of this cryptographic algorithm? Sometimes what they mean is, what's the size of the key? What's the domain, the number of keys that are possible? And it's considered strong if the domain size is very big, okay? So that's first thing, brute force. Second type of attack that we often see in cyber is called a heuristic attack. Now, heuristic attack's a little different. That's where you're using your intelligence, you're using knowledge, you're using something called a shortcut. So where brute force, I write a program or I do something that runs through every possibility. Heuristic attacks, you say, I don't have time for that. I can't do it that way. I need a shortcut. I need some way of making the amount of time to attack your system reduced. Now, the way we deal with heuristic attacks on the offensive side is not with size, but with complexity. I try and make whatever my scheme is that you're trying to break so complicated that you can't use your intelligence. Now, let's put those together. Brute force is about size. So if I see something that has a weakness in terms of, say, number of keys in crypto or the number of possibilities in terms of guessing, then that brute force nature would lead me to follow that approach. But if I see that you've accounted for that, then I'm going to use my intelligence and see, wow, let's see if we can find a way to break this system without having to try all the possibilities. So for example, let's take a dumb crypto example. If I said, you're 3 characters, to the keys, then I use brute force. But if I try and, make the key length real big, then the question is, can I figure out the algorithm? Are you doing something really dumb? If it's a function, is f of 2, 4, f of 3, 6, f of 4, 8. I don't need to go through all the possibilities to see that you're doubling the domain input. So complexity and size are the 2 ways that we deal with these main 2 types of cyber attacks. Brute force dealt with by size, heuristic dealt with by complexity. Keep that in mind. Thanks. So the art and science of creating codes is called cryptography. We're going to have a lot of fun learning basic cryptography in this course. You're going to come out with an understanding of how it all works. But the corresponding art and science of breaking codes is called cryptanalysis. So if you're making codes, you're doing cryptography. If you're breaking codes, you're doing cryptanalysis. And it's a good case study as we learn more about cyber attacks and think about them in the context of different taxonomies. Now, it turns out there's 3 strategies that we can follow for cryptanalysis. We'll take them in order. The first is called ciphertext only. That's where you, the attacker, are looking at a stream of encrypted data and you have absolutely no hints as to what's in there. You just see the encryption and you have to come up with some means for breaking the encryption. And in a previous video, we said one possibility is you do brute force attacks. You try and decrypt using every key you can think of. Another is to look at the encipherment. We call that ciphertext, encrypted text. See if there's something in there that we could figure out to somehow do the reverse of the encryption, which we would call decryption or cryptanalytic processing. So that's the hardest. Ciphertext only is the hardest case of cryptanalysis. No hints. Now, there's a second possibility, and that's where you do have a few hints. Like some crazy, you can imagine having a piece of paper that has some English text on it and having next to it the encrypted version of that. And you get hints, you look and you go, oh, so that encrypts to that, I get it. And in computing, we think of that more as the challenge response between Alice and Bob. So a lot of times encryption is implemented as a function so that one entity, Alice, lobbing over a challenge to Bob and getting back a response is like sending plain text and getting the encrypted ciphertext back. You follow? If Eve is watching this, she sees the plain text, she sees the ciphertext, it's a hint. It may not give you the whole function, it's certainly not, but it's a hint. It's not nothing. And we call that case known plain text. So ciphertext only, no hints. Known plain text, hints. Follow? Now there's a third case. And that's where I actually have the encryption function. I go break into your building and I take your encryptor and boom, I drop it down. Now, obviously, encryptors are not big pieces of equipment, but you get the idea. If I have the encryption algorithm, then I create something known as a code book. That's where I can literally feed input to the encryption function, look at the output, the corresponding encrypted function, the ciphertext, and write it down. And then I feed another input, encrypt it, write that down. And I do that successively over and over and over and over again and build up a code book. Now you would think, my gosh, if I can build a code book, I have you. I'd have the whole, I'd just sit there and build the code book and I'm done. How do we deal with something like that? Now, what did we say earlier was the type of attack that involves doing things over and over again? Brute force. And how do we deal with brute force? Size, right? The complexity of the algorithm is irrelevant if I'm building a code book. I don't care how clever your scrambling and transposition and other types of mathematical functions are, if I can just feed things in and read what comes out. But the one thing I can't deal with is if you've made the domain so enormously large that it would take from now until the end of the universe to build the code book. Let me say that again. If I can build a domain size big enough that for you to build a code book would take from now until the end of the universe, how motivated are you to even begin? It makes no sense. Size is the way we deal with brute force attacks. So let's keep those 3 things in mind. We have ciphertext only, known plain text, and chosen plain text, that third case where we're building code book. Obviously, code book is the easiest of the 3, but if I make the domain size big enough, then you're going to have trouble. It's a good case study in thinking through another taxonomy, yet another taxonomy around cybersecurity. We'll be back in a little bit with another session. So I want to do an example now, a real example of cryptanalytic attack, okay? So now let's start with the idea that we're going to have an encryption function, and cryptographers would call it a cipher. That's what they like to use. So we're going to have an encryption function. It's not be a very good one. It's going to be a replacement or substitution cipher where I take one character, replace it with another one, okay? Think letters. I take one letter, replace it with another, okay? And we're going to use probably the simplest of all substitution ciphers, the so-called Caesar cipher, where I'm just shifting letters in the alphabet. Let's say I'm shifting each English alphabetic letter, 2 slots forward. So A becomes C, B becomes D, and so on. I get that that's not a very good encryption function, but it'll illustrate the type of attack that I want to show you, because there are clever ways to sort of combine brute force with heuristic into a program that allows you to decrypt almost like magic based on ingesting data. Let me show you how this would work. Now, all of you know, that if I look at a frequency distribution for an alphabet, and we'll use English as the example, then there's going to be great predictive aspects of that frequency. For example, in English, the letter Z or Z is certainly not going to be seen as frequently in English sentences or talk as the letter A or the letter E or the letter R. And we can be very mathematical about it. We can lay out the exact frequency distribution of the English language. We can lay that out, okay? So we know that. And we know that if I start with a little sentence and start counting up letters, you know that it's not going to uncover the frequency distribution immediately, right? It takes time. So as I ingest a sentence, paragraph, a page, 10 pages, an entire book, by the time I get through the entire book, just counting letters and building the histogram, I'm pretty sure we've turned over the frequency distribution. We've created it. The more data, the more exact match we have to the frequency distribution. That makes sense? Now, if I'm doing a ciphertext only cryptanalytic attack on a substitution cipher that shifts the alphabet forward a couple, then here's what that means. Where you had intended to say apple, and it would have been A-P-P-L-E, well, when you encrypt that, A becomes C, right? And P becomes R, and the second P becomes R, and so on. Shifts forward. Now, if I take that stream of encrypted output and I start building a histogram of that, here's what happens. The letters will magically create the histogram, the frequency distribution of the English language, but for the letters that they were intended to be. Like the idea would be that now A, if it's a C, then where I see C's, it becomes A in the frequency distribution. You follow? Or P becomes R. So whatever I typed as my book, my English book, A, B, C, the frequency distribution is going to be the way it was intended by the writer. But when I encrypt it, when I shift the letters, that frequency distribution is preserved. And as I ingest the ciphertext, I can write a Python program, or I can write a C program, or whatever, that just indests the data, builds the histogram, matches it up against the frequency distribution, and voila! A ciphertext-only cryptanalytic attack using brute force ingest. That's a lot to say, but I think you understood what I said. That's kind of cool, right? Write a program that does the cryptanalysis in an automated way. Keep that in mind. It's kind of fun. It gives you an essence of how we might use computers and systems to combine brute force, heuristic, and other types of things into very effective cyber attacks. So we'll see you next time. Hi everybody, Ed Amoroso here, and for this week's video interview, I'm here with a very good friend of mine, Jose Dominguez, who is the CISO, the CISO for TD Ameritrade.
Good to be here.
That's a great job.
It's very exciting and rewarding.
Chasing bad guys all day long?
More like defending. I think they're the ones that are running and trying to break down our walls. So.
That's awesome. Now, in our learning community, we have a lot of young people who probably would like to know how in the world do you get to the point where you can have a cool job like that? Tell us a little bit about your background,
Sure.
how you kind of got interested in tech and so on.
Sure. So, mostly in high school and junior high school, was pretty good in math. But back, I'll date myself a little bit. Back in the 70s and 80s, there were no PCs, right? But then when I got to college, it was right around the same time that the IBM PC had come out, Microsoft with DOS had come out. So my parents thought I was going to be a doctor. I started taking electives around programming languages, and from that point on, I said, wow, this is a whole new frontier. The stuff you can get out of a machine to just, whether it was Fortran or PO1, some of the old dead languages, it was just, I never looked back. So that's how really I got into technology.
Do you remember your first computer? Remember what it was?
I did. It was I think a PCX 64, had 64 KB memory,
Right.
a floppy drive, and a 640K resolution
That's kind
on
of
the
cool.
screen. So we've
cool.
come a long way.
Now, as you sort of progressed, did you find yourself more interested in business and technology? Because you do a lot of the above, all the above. What was your path to kind of your career?
Sure, mostly technology, right? It was really programming and understanding applications that morphed into the business, right? So, I got to admit, when I was a 15-year-old, my first summer job was delivering stock certificates. Back then, there was no electronic settlement, there was no internet. We only had ARPANET. Right. So most of the financial firms dealt with physical security. So while I was learning all these computer languages, I started working at brokerage firms, financial firms. And that's how I really started getting into business. Security, I got to tell you, it was 2 books I read. One is The Cuckoo's Egg. I think it's still out there. I think it was Stoll that wrote it. And the other one was, in the late 80s, The Puzzle Palace. James Banford. NSA. He actually was able to publish what he did at the NSA all day long. So those sort of piqued my interest in security, but I never got to apply it, right? So I kept an eye on that. But I was really more focused on delivering value to the business through programming and understanding how the business flowed. I've been at brokerages for about 30 years. And then security, maybe 4 or 5 years ago, the opportunity came to me from my management where, the security had morphed less about technical and more about risk management, right? So they said, well, we got somebody here that knows technical. We have somebody here that understands how the business operates. What a perfect fit to sort of make risk decisions, because at the end of the day, that's what it really comes down to. What framework do you have, and how do you make those risk decisions, right? For some of your students, you may think, what's he talking about? That's pretty easy. It's 0 or 1. No, that's the easiest risk decision, where it's black and white. Speeding ticket. You went 55 miles an hour, you went faster, you get a ticket. It's a lot harder to quantify with that risk. And then on top of that, to sort of combine it with what the potential revenue and potential reward of that risk is, that's where it really gets tricky. And we find in the security world, we're doing that all day long. Are we allowing people to have connectivity to LinkedIn? Are we allowing people to have connectivity to Twitter? Things that you take for granted, but have some downside potential as well. And we're constantly trying to mitigate that risk.
Must be exciting kind of being in charge of security for a financial services firm. I mean, that's pretty consequential if something happens. I'm guessing you have to be on your game every day.
Yeah, because we have over 800 billion in assets. We have about 6 million customers, and we have about 6,000 associates. So we're constantly protecting the data. We're trying to constantly protect those assets because our customers and our clients are the number one reason we exist, right? We want to protect that information. And we have less folks trying to get our intellectual property. It's a pretty commodity business, but it's people trying to get information about the clients or actually get their money. I think that's the biggest threat that we have. But it's 24 hours a day, 7 days a week. It's you don't get any days off.
Now, I know you guys hire a lot of people, young people, people with experience and so on. Well, when you're interviewing or considering somebody, what do you think about? Like, what are some skills that you think are that impress you for cybersecurity, say, in finance?
So the number one thing I always look for is passion, right? Do you have a passion and desire to do well, right? That's the number one motivator that I would see. And then I look for technical skills, right? I found this true in my programming career, where languages changed every 3 or 4 years, whether you were PO1, whether you were Java, whether you were Angular, Backbone. Those languages kept changing. What I was looking for was someone that would have a technology background, and whether it was with networking, whether it was programming, whatever that technology background, understand the capabilities and how technology can leverage and maximize the firm's potential, but have, be able to quickly adapt to things that change. So I try to always learn technology first, and then I tell, folks that are starting early in their career, learn your business, right? How your business operates. Are they on a 5-day trading cycle? Are they on a 24-hour banking cycle? How does that business operate? Will leverage your technology to a net degree. Right?
So almost think like 3 different pillars, like the a technology base, the business base, and then security. Like if you put those together, is that the right formula, you think?
Perfect. But I think you need to understand the technology of what your company uses, understand how it uses it for a business, and then if you have both of those rings, then that top ring is how do I now try to protect and secure that, right? We don't get to play offense in security. It's all defensive. And we got to understand what we're trying to protect and in what different ways.
You look at threats every day.
Yep.
I'm going to probably look at them all day long every day, including weekends and nights and so on.
You bet.
Well, if you step back and look and you were trying to comment on the trends, is it just everything getting way worse? Is it getting different? What do you think? You must get asked that question a lot.
Yeah, and it's getting way worse, but it's also the speed to market of getting worse, right? It's, I guess the best analogy I can try to use, and for your students, they may not remember this time, but it was airbags, right? So airbags only existed for the high-end vehicles. Right. As time went on, it was almost like trickle down. Every single car came with airbags. And what we're finding is with the fraudsters and the bad actors, technology that was only nation state is easily turned into a commodity that's given to a lot of, individuals. So that speed where, the individuals will have sort of, we call them, almost like weapons of mass destruction and how they can use them. That and just how much is available technology-wise, right? One of the things that we saw a few weeks ago or a couple of months ago was the Mirai botnet, right? So your students can Google this, where with the Internet of Things and with things being even more connected, you're able to leverage that and then publicize it and let others around the world be able to use that tool, where you can actually do a DDoS attack using security cameras. I mean, think back years ago, nobody had a security camera at home. Nobody had their TV hooked up to the internet. So this interconnecting of just about every single device, and as a society, our dependence on technology, it's got some great things. It's also, though, got some holes where certain bad actors can take advantage of that and sort of use it for a negative reason. So I'm not, not saying we should be Luddites and get rid of technology. By all means, the rewards are great. It's just getting more and more difficult to be able to do that in a secure method.
But that speed of attack means the speed of defense has to keep up. That's got to be the hardest part.
It is, because it's how do I build a muscle memory, a capability that I didn't have yesterday, and I now need to react to it. That's, so you try to get some talented people. You try to sort of stay a step ahead and try to predict where the puck is going. You sometimes get it right, you sometimes get it wrong, but you can't wait to see what happens in the news to come up with your defense. You got to start thinking, where's this going? Where do I see a bigger risk coming forward?
Such good advice. I could listen to you all day.
I learned from some of the best.
You should be writing a book on how you kind of get to be a CISO.
After I finish all I got to do over the next 20 years, perhaps. But thank you.
Well, listen, on behalf of our whole learning community, thanks so much for taking the subway over to visit with us. I hope you enjoyed visiting us here at NYU.
Absolutely. I grew up in Brooklyn, over in Bay Ridge, so I love NYU coming to Brooklyn. It's a big thing.
Thanks so much for coming.
My pleasure. Thanks, Ed.
Appreciate it. We'll see you next time. Hi everyone, Ed Amoroso here, and I want to welcome you to this module. Now our goals in this module are to kind of go through some more advanced attacks. I want to look at worms and DDoS attacks and kind of dig into them a little bit and get some perspective on where the offense, seems to be headed. There's certainly more intense attacks than existed at the beginning of cybersecurity. There's a couple of cool papers that I'd like you to take a look at to complement the learnings here in the module. One is a Wired magazine article. It's all about Andy Greenberg, who's a reporter at Wireless, or at Wired magazine. He he writes about his experiences being in a Jeep as hackers, essentially live take over the Jeep while he's on a highway. You can question whether it was a good idea to actually do that on a live highway, but I do think you should read Andy's article. And then second, there's a sort of a biographical piece about one of the real pioneers in building attack and offensive weapons, H.D. Moore. Now, I say weapons, he probably would say, gosh, they're not weapons. They're tools that help you demonstrate the security of your system. H.D. Moore is one of the best, and Metasploit traces its lineage back to H.D. as being the real founder there. And we got a little paper that we found that kind of takes you through a little bit of his journey in the cybersecurity industry. So I think you'll like that paper. Now, there's a couple of optional books that we recommend that you make use of during this module. One is an ebook that I wrote with my son Matt. It's called From CIA to APT: An Introduction to Cybersecurity. You can get it on Amazon. Again, optional. But if you decide to read along, chapters 5 and 6 would be good ones for you to take a look at. And then I do think it makes sense for you to have a good, solid TCP/IP textbook on your professional bookshelf. It's optional for the module, but recommended. And if you need one, Richard Stevens, I think, has one of the best books ever written on TCP/IP, TCP/IP Illustrated Volume 1. And if you look at chapters 5 and 6, I think they'll help you a little bit with this module. There's a couple of TED Talks that I think you should watch along with your study in this module. One's by Pablos Holman, and it's about, basically a top hacker talking about how he does things. I think it's really quite good. And the second is an old friend of mine, Avi Rubin. He's a professor at Johns Hopkins, and he he gave a nice TED Talk called "All Your Devices Can Be Hacked." I think it's just delightful. A little frightening, but really quite a good talk. So I hope you'll take advantage of these resources as you're learning through this module. And I hope you learn something. I hope you enjoy the material we put together for you. Thanks a lot. Hi, folks. Ed Amoroso. I want to tell you a little bit about some issues that came up on the public internet in 2003. And let me start with a story. Right around January 2003, a lot of us were woken up on a Saturday morning by a bunch of texts and calls and notices that the internet was going nuts. And in particular, it was the packets on a UDP port that were building up like crazy, just completely exploding, hitting gateways, taking out networks, taking out systems. Now, you'll recall in an earlier lesson, we talked about the way a worm program works. And this issue in 2003, it was called the slammer worm, was really one of the first instantiations of a worm that would affect the whole internet. And you remember there were 3 ways that a worm worked. We find a system, copy the worm program to the system, and then remotely execute. And it cascades. So what was happening in January 2003 is we were seeing the effects of this cascade across the internet on UDP. So a lot of questions emerged. Number one, what do you do about it? I mean, when there's UDP packets hitting a gateway, the first question that any security administrator would have is, what's attracting this in? Why are these UDP packets coming in? Are they good? Are they errant? Is this denial of service? It's that kind of chaos that typically characterizes what happens during defensive work when a worm is ongoing. Second thing that people noticed is that a lot of the intrusion detection systems and defenses that you have for small scale problems don't work for a worm. I mean, think about it. On a small system, when you have intrusion detection, firewalls, the kinds of things that are probably very familiar to you, particularly if you have them on your PC, they just don't work when there's a barrage of UDP packets coming at you. So it was one of the first times we all noticed, and back in 2003, that we had to come up with ways of doing intrusion detection and intrusion mitigation on a larger scale, meaning across the entire internet. And this worm of 2003, this slammer worm, really woke a lot of us up. I mean, it just went nuts. Now, a couple of interesting things about this worm. One is that when we went back and looked, when we looked at the metadata associated with this worm and with UDP traffic on the internet, what we noticed is that the worm actually launched, you can see on the chart, at the end of January. The worm kind of spiked. There was a gigantic increase in UDP traffic, but there'd been attempts earlier through the month of January, presumably on the part of whoever was writing this worm, to try to launch it sooner. It was a very interesting observation because it gave us quite a bit of hope that perhaps by observing metadata in large scale on the internet, that might be the secret to intrusion detection, intrusion prevention on a large scale. So think about that. So instead of indicators on a system or in an audit log on a PC or on a server, the question emerges, can you collect that kind of data on the internet? Can you collect metadata at internet gateways, at peering points, at places where service providers potentially are looking at public traffic, and use that as an indicator that maybe something's brewing? It was way back in 2003, and I'm laughing because I'm guessing there may be some of you watching this who weren't even born then. But that 14 years ago, we had that issue with this thing just exploding. We learned a lot of lessons. Now, just sort of to summarize here, the slammer worm was one of the first times we saw broad cascade of a worm affecting internet infrastructure. Second, it demonstrated that a lot of the techniques that we use in the small don't work in the large. They're just not going to be the same kind of effect. And third, that maybe there's some hints in the early metadata collected across networks that something might be brewing. So this gave us a lot of hope in 2003 and led to a lot of companies and organizations and universities and researchers investing more time, effort, and money into something that we would now call large-scale intrusion detection, intrusion prevention. It's one of the ways that we stop other kinds of attacks, denial of service, and so on, and we'll get to that in some later discussions. But for now, I want you to understand that this SQL slammer worm was kind of the beginning of the modern era in large-scale internet service and internet infrastructure attacks. So we'll get more into this in some additional videos. But for now, I think that's a key lesson that we take back from the SQL slammer worm of 2003. We'll see you in the next video.